In this video, I'm going to show you exactly what an ESP32 is, how it compares to other popular hardware like the Arduino, and walk you through its key features. Plus, we'll roll up our sleeves and write a simple program to get an LED blinking. But first, what is an ESP32? The ESP32 is a low-cost, low-power microcontroller that packs a punch with built-in Wi-Fi and Bluetooth, making it a go-to choice for DIY projects and IoT devices. Now, the actual ESP32 microcontroller is this within the casing right here. It's embedded within this larger board that's commonly called a development board or a DevKit. There are many versions of the ESP out there, produced by different manufacturers. That's because the creators, Espressif, made a genius move. They open-sourced their reference designs for their microcontroller, allowing companies to modify and build their own versions of the board. Let's take a moment to compare it to other popular hardware that you might have heard of. First up, the Raspberry Pi. Microcontrollers like the ESP get compared to the Raspberry Pi a lot, but only because they can both control external components like LEDs and sensors. However, they're very different. The Raspberry Pi is a fully fledged microcomputer with an operating system, typically Linux. It's meant for complex tasks like running servers, media centers, or even small desktop applications. But that power comes at a cost. The Pi usually requires more energy, making it less ideal for low-power projects. The ESP32, as a microcontroller, is built to handle small, specific tasks, such as getting data from a sensor and sending it somewhere. It consumes relatively little power to the point where they can efficiently run off batteries. Now let's talk about the Arduino Uno. Like the ESP32, the Arduino is a microcontroller, but the performance difference is huge. The Uno uses an 8-bit ATmega328P processor, while the ESP32 features a dual-core extensor 32-bit LX6 processor. And it's not just about processing power. The Arduino Uno only has 2 KB of SRAM and 32 KB of memory, whereas the ESP has significantly higher specs with 520 KB of SRAM and 16 MB of memory. There are loads of different types of ESP32 boards out there, such as the ESP32 CAM for camera-based projects, the ESP32 S2 for low-power applications, and the ESP32 C6 for home automation, plus loads more. But for today's project, we'll be using the most common one, the ESP32 DevKit C. So let's take a closer look at the DevKit C. In addition to the microcontroller part we covered earlier, it has a micro USB port to connect to a machine during development, USB to UART bridge to allow us to interface with the board from a computer, a voltage regulator to ensure a stable 3.3 volt power supply, the antenna for Wi-Fi and Bluetooth comms, and finally the pins, which are crucial for connecting the ESP to external components such as LEDs and sensors, and also supplying power to the board. The ESP can be powered through the onboard USB port, typically used during development, the 5V pin, or the 3.3V pin. If you're powering through the USB or 5V pins, the onboard voltage regulator steps down to the required 3.3V. This flexibility makes the ESP adaptable for different power sources, from normal wall plug sockets to battery packs. The ESP operates on 3.3V. This means both the ESP and its connected components must also run on 3.3V. While many modern components are designed for 3.3V, if you need to use a 5V component, a level shifter is required to avoid damaging the board. However, it's generally best to stick with 3.3V components where possible. So what components would you want to connect to the ESP? One common use case is in IoT projects like an environmental monitoring system. You can connect sensors such as the BME280 or BH1750 to measure temperature, humidity and light. Thanks to the built-in Wi-Fi and Bluetooth, you can easily send this data wirelessly to a server or app, or even another microcontroller. No matter what you use the ESP for, external components like these are all connected in the same way, using the pins on the board. Each pin has a specific function, as shown in this pin-out diagram. But for now, I'll just show the basics, as that diagram contains a lot of information that you might not need to know until you have a specific use case for some of the different features. Most boards have 38 pins. Of the 38 pins, some are dedicated to power or ground, and some have special functions that limit their use. This leaves 26 GPIO pins, or general purpose input-output. And we use these pins to connect and control external components through our code. Connecting a simple component like an LED can be connected to any of these. However, some components need to transfer data back and forth with the ESP. For this, we use different communications protocols. For example, a GPS module will often use the UART protocol, which is serial data transfer, which only uses 2 GPIO pins, GPIO 1 and 3 by default. And some LCD displays can use the I2C protocol, which also only requires 2 GPIO pins, GPIO 21 and 22 by default. Now here's where the ESP32 really shines. While certain pins are set as defaults for protocols like UART and I2C, the ESP32 allows you to remap most of its GPIO pins so that you're not tied to specific ones. Depending on your project or layout, this can help make things easier and cleaner with your wiring. During development, most people use solderless breadboards. This allows you to quickly connect components without needing to solder, making it easy to experiment with different configurations as you develop your program. Later, for a more permanent and solid device, you can move to a PCB and solder your components in place. Now the basic overview is done, let's create a simple Hello World. For our Hello World project, we'll connect an LED to the ESP and make it blink on and off. This will introduce how to wire components to the ESP and also how to upload code to control those components. First, you'll need to get ready the following items: an ESP32 board, a breadboard, a LED, some jumper wires, and a micro USB to USB or USB-C cable, depending on your machine. I highly recommend using these jumper wires with hard plastic pin headers because they're much easier to insert into the breadboard compared to plain wires like these. These can be tricky to work with as they're sometimes hard to get into the holes. We'll start by wiring up our LED to the ESP. The plan is for us to create a circuit with the ESP supplying power to the LED. Let's add the ESP32. This can go across the middle of the board, but you'll notice there's not enough room on both sides for the wires. This isn't ideal, and I usually get around this by having the ESP span across two breadboards, but we don't need to worry about that for now. Now we can add the LED. This can go over here across the middle, which allows the circuit to span across these two horizontal rows. We're adding the anode, the long leg, which is positive, and the cathode, the short leg, which is negative, into the breadboard. We don't have a closed circuit yet until we add the wires. Next, we'll connect a jumper wire from GPIO pin 17, which we'll program in our code later. We'll connect this to the anode, or the positive end of the LED. Then connect another wire from the cathode, or negative end of the LED, to the ground pin of the ESP. This completes our circuit. With everything wired up, nothing will happen just yet because the ESP doesn't have any instructions. Now let's write some code to bring the LED to life. First thing to do is download the Arduino IDE. It just so happens that Arduino not only make their popular microcontroller, the Arduino Uno, but they also created one of the most popular development board code editors. Once you have the IDE installed, depending on your version, it may not have support for the ESP32 out of the box. To add support, head to the official Espressif site using this link here. I will add the link in the description below. On the official Espressif site, scroll down and you can see a URL here. Go ahead and copy that URL, then go back to your IDE and go to Settings and click this button next to Additional Board Manager URLs and paste the link in there. Then go to Board Manager and type ESP32. We're looking for the boards package by Espressif Systems, which is this one right here. Go ahead and click Install. Once installed, you can go up here to Tools, Board, and ESP32 is now listed because of the package we've just installed. Look in there and select your board. I usually select the ESP32 Dev module. Last step before we write some code is to check that our board is being recognized by the IDE. First, make sure that the ESP32 is not plugged into your machine. Now in this drop down here, you may see a default port listed. This could be Bluetooth or something like it is here with mine, but it doesn't currently show our ESP32 board. Now if we plug our ESP32 into our machine, we want to see if it appears in this drop down. If it does, great, it means the USB to UART bridge is being recognized by our machine. If nothing happens in this menu when plugging in the ESP, it means the board is not recognized and you'll likely need to install a driver. This is the driver for the machine to interface with the USB to UART chip on the board, which on the ESP DevKit C is the CP201X. You can find the driver on this link. I will also add this to the description. At this point, we have an optional step where we can click here to just upload an empty program to the ESP32. If it uploads successfully, we won't see anything happen, but we'll know that the machine is able to upload our code without any problems. If there is an issue at this point, one more thing to try is to press the ESP32 boot button when you start to see the dots appear here. This ensures that the board is in boot mode, but is not required for most boards. Now let's write our code. The Arduino framework provides us with these two functions, setup and loop. The setup function is called just once when the microcontroller first powers up, and is used to initialize variables, pins, and library functions. The loop function runs after the initial setup and runs continuously, allowing for the microcontroller to run its program. For our setup, we want to initialize the GPIO pin we connected our wire to earlier, which was pin 17, and configure this as the output, meaning this pin is configured to send voltage out to our LED. It doesn't send the voltage out yet though. This is where the loop function comes in. In our loop function, we want to add code to blink the LED on and off. We can do this by using our digital write function to send power to the LED. The function has two parameters, the pin number, which is 17 in our case, and the voltage level, which we will add high. This will send voltage from pin 17 to the LED, turning it on. Then we use the delay function to pause execution of the code for 1 second. Then we use the digital write function again, but this time the second parameter will be low. This will turn down the voltage and turn the LED off. Finally, we add a 1 second delay again. This will allow our LED to blink. Now we can do a little tidying here. Let's create a variable for our pin number. This will allow us to reuse this variable and stop repeating the pin value. It's not too important for such a small project like this, but as programs get bigger, it allows us to easily change the pin number in one place, rather than going through our code and updating in multiple places. Now that the code is done, let's go ahead and click Upload again. This will upload the fresh program up to our ESP32. As soon as we can see that the upload is complete, if we look at our ESP, we should be able to see the LED now blinking on and off. One thing to mention about our setup here is that I purposely made it as simple as possible and not included a resistor. A resistor is generally preferred when connecting things like LEDs to our ESP because it limits the current going from our board to the LED. This would help protect both the board and the LED from any potential current surges. As we've just uploaded code from our machine, we are using the machine as our power source. But now that the ESP contains its program, we are able to unplug it from our machine and connect it to a different power source, such as a battery pack, or even directly into a plug socket in our wall. That about covers it for this video. If you've enjoyed this, please like and subscribe.